All right, we're back. We are on page 1 of note 6 of Calc C, and we're still talking about infinite series, and we're still trying to figure out, like, do they converge, do they diverge? We've talked in the past about Taylor polynomials, which are going to become Taylor series, and then we did geometric telescoping. We talked about the nth term test for divergence. It can only tell you if a series diverges. We talked about the integral test, and that led us to P series. And now what we're going to do is talk about something called a comparison test. So this one requires a little more like nuance, I guess. It's a little less direct. So a comparison test. Well, what we want to do is first establish some sort of comparison that we can make. So if you look at it, well, if you look at something, for example, right? If we try to compare 1 over 2 to the n versus 1 over n times 2 to the n, right? So I'm claiming that 1 over 2 to the n is definitely bigger than or equal to 1 over n times 2 to the n. And the reason that I'm saying that is because if n is greater than or equal to 1, which is kind of a given because we're going to do summations from 1 to infinity, if n is greater than or equal to 1, then n times 2 to the n is definitely bigger than 2 to the n, which means when you take reciprocals, it'll flip the relationship. So what we're going to do is we're going to compare this series from 1 to infinity with this series from 1 to infinity. Now, both of them always spit out positive terms, so it's not possible for this thing to for the sum to diverge to negative infinity, for example. Like you're adding up positives, you would have to get a positive. So you don't need to worry about the one series like dipping down below 0, going and spiraling off. Instead, what I did was I made this little GeoGebra thing. It's not really hard to visualize this, but what we have here is so 1 over 2 to the n and 1 over n times 2 to the n, when n is equal to 1, they're both 1/2. You get the exact same term, and you can see here it's the first term, you get 0.5 for both of them. I'm also drawing a little segment just because for whatever reason, when I look at this, I have trouble vertically aligning things. I don't really know why that's the case, but I'm going to let the number of terms increase. So if we go here, you can see that this blue one is, the color choice is terrible, by the way. I should have done something. Maybe I'll just do it now. Hold on. Let's change this to what? All right, I think you can tell, right? So the orange now is 1 over n times 2 to the n, and the blue is 1 over 2 to the n. So 1 over 2 to the n is above, and then 1 over 2 to the n is above, 1 over 2 to the n is above. And you can see that's always going to be the case. 1 over 2 to the n is always greater than or equal to 1 over n times 2 to the n, as long as n is going from 1 to infinity. So since that's the case, I'm going to go back to the notes. Since that's the case, if 1 over 2 to the n converges, it's not possible that the other one doesn't converge. It's definitely smaller than something that is converging. So this is the basis for the comparison test. So what we have is we are looking at this, and we know something about this. This is a convergent geometric series. And we know that every single term of that is greater than or equal to the corresponding term of this. Since we know that the purple one converges, we know that the other one must converge also. It's as if we put a lid on it, right? Like it was trying to go somewhere and we're like, oh, no. We put a lid on it and we just like stopped it. It can't spiral out of control. It must also converge. So that's basically what the direct comparison test says. So let's take a look at the actual, verbiage or whatever. So this will be our 6th series test, and it's called the direct comparison test. So the problem with using it, it's not really a problem, but it's kind of a problem, is that we were able to establish this relationship, right? And it was pretty clear. And the reason we said that that was true was that it's very clear if you're looking at 2 to the n versus n times 2 to the n, like you're multiplying 2 to the n by some integer, it's obviously going to be bigger than it started out as. So we were able to establish that. If you can't establish that, this is a little tricky to use. But if 0 is less than or equal to a to the n, which is less than or equal to b to the n, okay? So the 0 is the minimum, like they're always positive termed, basically. These are positive term series. And then for all n, a sub n is just smaller than b sub n. There's 2 things that could happen. So if B sub n, the bigger series. So if the bigger series converges, then so does the smaller series, right? So if the top one converges, the bottom one has to converge. The other argument is also true. If you happen to know that the bottom series, the smaller series, diverges, then by default, it's going to shove the bigger series off to divergence as well. So if the smaller series diverges, so does the bigger series. And I think of one as like putting a lid on it, and then the other one is just kind of like shoving it up to basically infinity. So that's our direct comparison test. All of it hinges on your ability to show that A sub n is less than or equal to B sub n. And that's not always easy to do. One of the ways that we'll do it frequently is to use this inequality property of inequalities. I don't know what you want to call that. I think it's property of inequalities. As long as A and B are not equal to 0, if A is greater than B, so I don't know what I'm really doing here. I'm going to make sure to highlight the, highlight the colors, right? So if A is less than or equal to, nope, if A is greater than B, then 1 over A is less than 1 over B. And if you're confused about that, just use numbers. So it's not like a big secret, right? Like, what do we got here? We got 5 is greater than 1, but 1/5 is less than 1 over 1. Maybe let's use 2 so that at least we're like flipping something. There we go. So 1/5 is definitely less than 1/2. So when you take a reciprocal, it changes the relationship, and that's going to be important for us. So let's see if we can do this one. A lot of our direct comparison problems are going to be like pretty straightforward because I don't want to get bogged down in the comparisons, like determining the relationship. And also, I almost never use direct comparison unless I'm told to because of the next test that we're going to learn. But first, let's see if we can do this. So first, I'm thinking this looks a lot like, so here's how I usually do these. This part, it looks like just 2 to the n, right? I mean, there's, if n is infinitely large, n plus 2 to the n versus 2 to the n, what's the difference, right? So it looks like 2 to the n. And I know that n plus 2 to the n is definitely going to be greater than or equal to just 2 to the n for n greater than or equal to 1. So that's got to be true. So now let's use the property. And also, both of them are greater than or equal to 0. So we need that to be true, positive terms. Take reciprocals. This is definitely less than or equal to 1 over 2 to the n. And then also, this is true. So we're stuck in between 0 and 1 over 2 to the n. We know that the sum of 1 over 2 to the n converges. And then you want to say why. So why does this converge? Well, it converges because it's geometric with r equal to 1/2, which is less than 1. So 1 over 2 to the n converges. Therefore, 1 over n plus 2 to the n, which is a smaller series, must converge to something smaller than whatever 1 over 2 to the n converges to. So this converges as well. We don't know what it converges to, but I'm going to say it by, I always abbreviate this as DIRComp, which I don't know. I also kind of just like saying it. So this converges by direct comparison. And we don't know what it converges to, but we know that it converges to something smaller than whatever 1 over 2 to the n converges to. So this was 1 to infinity, 1 to infinity. So what does that converge to? Let's see. That would be the first term over 1 minus the ratio. So 1. So this converges to exactly 1. This converges to something smaller than 1. We don't know what. We just know that it definitely converges. So that's a kind of a textbook example of using the direct comparison test. It was easy-ish because n plus 2 to the n looks suspiciously like 2 to the n with just a little bit of extra tacked on. But honestly, most of them kind of look like that. So I'm going to be back in the next video, and we will do a bunch of practice problems. And so I will see you there.